Okay, today we're going to talk about the random variables and their distributions. And before we do this, let us discuss the previous lectures. So the previous lectures, we talked about the rules of probability. We talked about the additional rule and the multiplication rule. And when we're talking about the additional rule, it is important for us to know whether the events are mutually exclusive or not, right? So because depending on this, we're going to calculate the probability of the A or B using differently. So essentially, the probability of A or B is going to be equal to the probability of the A plus the probability of the B minus the probability of the A and B, right? And could you please explain me what does it mean that the two events A and B are mutually exclusive? They don't have the intersection, right? So the intersection between these two sets is simply empty, right? So that is why the probability of the A and B is simply going to be equal to the zero. So please note here that probability of the A and B means the intersection of these two events, okay? Because there is a different meaning of the probability of the A and B. So could you please give me some example of two events which are not mutually exclusive? So if you remember previously, we talked about the cards, right? Do you remember one event was choosing a jack and the second event was choosing a heart, right? These two events are not mutually exclusive because it is possible to choose the heart jack, okay? So can you give me another example of two events which are not mutually exclusive? Yeah? Uh, yeah, I mean, okay, you can make this with the cards. Can you give me some more, like, a different example, like not from the cards? Yeah, so I mean, we need to figure out the example where the items are going to have the two attributes. Okay, for example, we can create this set like this. So let's say I've got the class of students, okay, and some of the students have the ID 18 and some of them have ID 17. Okay, at the same time, so what I want is I would like to choose what is the event A is going to be choosing a student with the ID 17. Okay, and at the same time, I'm going to create another event B, which is going to be choosing a student who's female. Okay, so what do you think? Is it possible to have both of these events happening at the same time? So I'm going to choose one of you, one of the students. Is it possible to choose a student who's female with the ID 17? Yes, so in this case, these two events are not mutually exclusive events. Okay, so it is important for us to understand this. So at the same time, we talk about the multiplication rule, and you know that there are two versions of the multiplications, right? So the one version is when we're talking about with regard of the intersection. For example, what is the probability of choosing a person who is female and with ID 17, right? So you need to find the number of these people and divide this as the total number of the students. You're taking the intersection, right? But at the same time, it is more important for us to calculate the probability of the two events happening in the sequence, okay? So we talk about this. So if I say, so the easy example would be like choose, so choose two cards from the standard deck of cards, okay? And you can choose a jack first, then a queen, okay? So in this case, we're going to calculate what is the probability of choosing the jack times what is the probability of choosing the queen when the first card is jack already. Okay, so this is going to be the multiplication rules. So, well, this is going to be equal to the 4 over 52, right? Choosing the jack, times if you choose the first card without replacement, it means that you don't put this back into the deck, then the probability of choosing the queen is going to be different than if the event didn't happen, right? So it is going to be equal to the 4 over 51. Okay? So when the occurrence of the first event affects the occurrence of the second event, we call these two events as dependent. Okay? Because the occurrence of the first event is basically changing the probability of the second event. So this is very simple example of the dependency. Um, so when the two events are independent. So if I say, hey, so if I just change the experiment a little bit. by saying that I'm going to choose the card, then I'm going to put this back. So I'm going to do this experiment with replacement. So in this case, what is the probability of choosing a queen when the first card is the jack? What is this? It is the same as choosing the queen, right? It is going to be 4 over 52. Do you understand this? So this is the second case, right? So this is the another experiment. It is an experiment when you choose the card, the first card should be jack, okay? After, you're going to put this card back into the deck, and then you're going to choose the second card, okay? So what is the probability that the second card is going to be the queen? So how many cards we have? 52, right? Because we put the previous card back to the deck. How many queens we have? 4, okay? So these two probabilities are going to be simply the same if the two events are independent, okay? So do you understand what is the dependency and what is the independency? If the two events are independent, then the probability or the occurrence of the first event simply doesn't affect the occurrence of the second event, simply, okay? Cool. So sometimes we need to evaluate, for example, do you remember we've considered an example when you've got like 5 balls in the box, like 3 of them are red, 1, 2, 3, and 2 of them are blue. Okay, so now let's choose 2 balls without replacement. So basically, you choose the ball, then you're going to choose the second ball. Okay, so what is the probability that the second ball is blue if the first one is red? What is yeah. What is the probability if the first one is red? So you choose one ball. This is red already. You know this. Okay, you don't put this back into the box. What is the probability that the second ball is blue? Huh? 1 over 2, right? Or 2 over 4. Okay, so 2 over 4. Is that clear? Because the first ball is red. So there are 5 balls. You choose one of the balls. This is red. Okay, we know this. You know this. I didn't put this back. There are 4 balls left already in the box. 2 of them are red. 2 of them are blue. So then in the second trial, probability of choosing the blue one is going to be 2 over 4. Okay? So this is easy, but sometimes we are required to calculate the probability of the first ball is red if the second ball is blue. Okay, so that's going to be a little bit confusing and different. So let's assume that I'm going to shuffle the balls, okay? I'm going to choose one of the balls, and I'm not going to show it to you, okay? I will just hide this. Then I'm going to just put this box to here, and I'm going to choose the second ball. And you see, so all of this, so do you see the color? So this ball is blue, okay? The second ball is blue. What is the probability that the first one is red? Hmm? 6 over 20. How do you know this? Uh, no, it doesn't work. It is the conditional problem. It is not the multiplication rule. Okay? So I'm not asking you what is the probability that the second ball is blue and the first ball is red. I'm asking you, hey, the second ball is blue. You know this already. Okay? Do you see that this is blue? Okay? What is the probability that the first one is red? Okay? You see, so the first case was kind of easy, right? And the second case is confusing. So when we know this case, we know the answer for the 2 blue and 1 red. We know the answer for this case, but we don't know the answer for this case. We are going to use the Bayes rule. The Bayes rule is simply going to calculate this conditional probability for using this. Okay? So how it works, do you remember the formula? Can someone tell me how it works? So 1R given 2B. So one way to memorize the formula is like this. So you just need to swap the places of this conditional probability. It is going to be probability of the 2B given 1R times the probability of the 1R. Then the second probability is just simply going to jump over, okay? And everything is divided to what? To the probability of choosing the second ball to be blue, okay? So more or less everything here is going to be straightforward to be calculated, except this one. So probability of choosing the second ball to be blue. Okay. So what is the probability that the second ball is blue? Yes, Handamir? What is the probability that the second ball is blue? Huh? The second ball is blue, not the first one. The first one is blue, it's 2 over 5. Huh? Well, how do you know this? What is the probability that the second ball is blue? Is it 2 over 4? Maybe 1 over 4. Huh? Yeah, we should consider it. Well, it depends what is the first ball, right? Okay, so there are two scenarios. Either the first ball is blue, then you're going to choose the second ball is blue if the first ball is blue, or the first ball is red, and you're going to choose the second ball is blue if the first ball is red. Okay, so I just wrote down my words, my sentences mathematically like this. Okay, so there are two possible scenarios. Either the first ball is blue, then you're going to choose the second as a blue, or the first one is red, then you're going to choose the second as a blue. Okay, then we just need to sum these two probabilities. If you sum what you get is, so it's going to be 2 over 5 times to the 1 over 4. Okay, plus 3 over 5 times 2 over 4. Okay, so I'm going to put everything together to here. It is going to be equal to, um, so the first red is 3 over 5 times to 2 over 4 divided to 6 over 20, right? And here I've got like 2 plus 6, 8 over 20, 8 over 20, and this is going to be 6 over 8. Okay, so now you know that the probability that the first ball is red, if the second ball is blue, is equal to the 3 over 4. Okay, 75%. So this is why we need the Bayes rule. Okay, so let's solve this problem then on the Bayes rule. So we are going to do this together. So there are 3 balls, 3 black balls, and 4 white balls in the box. Okay, so please read this carefully. So we are going to choose 2 balls. Okay, when we choose the first ball, okay, if this is white, if this is black, so there are 7 balls in the box. 3 of them are black, 4 of them are white. We are going. Should I draw this? Oh, it is going to be difficult for me to draw the white ones, right? So 1, 2, 3, 3 black one, and let me draw the white one as a blue. Okay, 4 white ones. Okay, or 4 blue ones. So you choose one ball. If this is black, okay, you're not going to put this black back. You're going to put 2 white instead of this black. Okay, but if you choose the ball and this is white, you're not going to put this white back. You're going to put 1 black instead of this white. Okay, so now the question is, what is the probability that the first picked ball is white if the second ball is white? Okay, you understand this process? So you choose ball. If this is black, you're going to put 2 white. If this is white, you're going to put 1 black. You did this, okay? I did this, but you don't know what I did, okay? So I choose the ball, okay? I decide like whether if it is red or black, if it is white or black. Then I did this experiment. Then I'm going to put the box to here. I'm going to choose one of the balls, and you see that this is white. What is the probability that the first one is white? Okay, you have to calculate this because, again, we're going to use so-called Bayes rule. The first step on solving this kind of problems is to write down what we want. Okay, so what we want to calculate is, we would like to calculate what is the probability that the first ball is white if it is given that the second ball is white, right? So you see, so I could easily calculate this probability if these 2 events would be swapped, right? I could calculate the probability of the second is white if the first one is white, right? By the way, what is the probability that the second ball is white if the first one is white? So there are 7 balls, right? If this is wide, okay, so you're going to choose wide and you're going to put 1 black, okay? It is going to be 4 blacks and 3 whites, okay? And probability of choosing the second one as the wide is going to be 3/7, simply, okay? Easy. But this way, it is difficult. So that is why we are going to use again the base rule in order to calculate the probability of this probability. And the base rule, again, so you need to understand why we need to use the base rule, right? So we don't know how to calculate this probability, but we know how to calculate the version when they would be swapped. Then use the base rule. Okay, so this is going to be the guides when you have to use the base rule. So we are going to just swap their places. It is going to be the probability of the 2 wide, given the first one is wide, times the what? So this 1 wide is going to jump over from here, okay? And all of this divided is the probability of choosing the second one as the wide. Okay? And again, we are going to calculate the probability of choosing the second ball as the wide using so-called the law of total probabilities, because depending on what is the first ball, it might be different, right? So there are 2 scenarios again. So either the first ball is wide, and we're going to calculate the probability that the second one is wide. Either the first one is black, and we're going to calculate the probability that the second one is wide if the first one is black. Okay, so what is the probability of choosing the first one as a white? 4/7, right? There are 4 whites and 7 balls in total. If the first one is white, what is the probability of choosing the second one as a white? 3/7. Okay, so plus, what is the probability of choosing the first one as a black? 3/7, right? And if the first one is black, what is the probability of choosing the second as the white? 6/8, right? Because if the first ball is black, right, there are 7 balls, okay? You choose 1 ball. How many balls left? 6, right? And now instead of 1 black, I'm going to put 2 whites. There will be 8 balls, and 6 of them are going to be white, okay? So that is why probability of choosing the white is going to be 6/8, okay? Do you have a calculator to calculate all of these things? So now you're going to put all of the numbers to here. So this is going to be equal to 4/7 times to the 3/7 divided to the 4/7 times to the 3/7 plus 3/7 times to the 6/8. And if you calculate everything, it is going to be roughly 0.43. So this is how we can calculate the things. And again, so the key to solve such a problems is to write down the statements as mathematical expressions. Okay, so once you did this, it is like more or less straightforward, because all of the problems in this type are going to be solved like this always. Okay, cool. So this is about the base rule and the probability rule. So this kind of problems basically combines all of the rules which we have learned so far, like the additional, the multiplication rule, the conditional probability, and the base rule. So and starting now today and in our next few lectures, we're going to discuss about the random variables. So the random variable is obtained through the probability experiment, and depending on what type of the experiment we are doing, we are going to classify the random variables into the 2 types. So one type of the random variables is going to be called as a discrete, when we are going to obtain the result which are countable. Okay, for example, the number of the students in this group is the random process. Okay, so you can create an experiment. So every time, or for example, I can come every hour to this class and I can count the number of the students who are sitting here. And every time it is going to be random. So you need to understand that the random means that something which you cannot predict. Okay, so yeah. So, and this is going to be random, and this is going to be discrete random variable because I can count the number of the students. Okay, but there is another process. So there is another random variables which are called the continuous random variables, where where you're going to measure the output, not count. For example, you can measure. For example, so you have a couple of lectures today, right? And you know that all of your lectures are not exactly 1 hour, right? So all of them are going to be vary in their lengths. And this is again something which is random. You cannot know this before, okay? So and you can write down how much time it took for you for every lecture, okay? And this all of these numbers are going to be the continuous random variables because you're going to measure the time, okay? We don't count the time. Or for example, you can measure the time when your professor is late for every lecture, okay? So you can also measure this. Or you can measure the distance which you covered every day. You can count the number of the steps, but you can measure the distance which you covered. Okay, do you feel the difference? So all of these cases are the random variables, but you see that there is a difference between them. So there are discrete random variables and the continuous random variables. And we are going to we're going to talk about the discrete ones separately than the continuous ones, because the discrete ones have the special functions, so the so-called mass functions, the cumulative distribution functions, and so on. We're going to talk about this first, then we're going to talk about the continuous functions. Okay, so let me ask you a couple of questions. So the distance you travel by the full tank of the gas with your car. So you know that whenever you have the full tank of gas in your car, every time you travel a different amount of the distance, right? So it's a random variable. Okay. So what kind of random variable is this? Is it a continuous one or a discrete? Discrete, right? Because you count the distance. Yes. Yeah. It's continuous because you measure the distance. You cannot count the distance, right? Distance is something which is measurable, right? I mean, I usually measure the distance. I don't know about you. Okay, so distance is something continuous. Okay, I mean, it's so one. If it is confusing for you, so you need to always think about whether it is measurable or countable. Okay, so you don't count the distance. I mean, for example, kilometers, or you don't count the time. You measure the time, or you measure the kilometers, right? Or you measure the height. For example, I can go through the students here, okay? So of course, the values might be numerical, and they might be even the whole numbers, integers, but still they're continuous because we measure the height, okay? The number of the students in statistics class is again the random variable, and this is the discrete case. Okay, do you understand what's going on? Today we're going to talk about the distributions of the random variables. It is really important for us to understand what is the distribution of the random variables in order to make some predictions about this random process. Okay, so depending on the shape of the distribution, so distribution means like how the outputs of your experiments are distributed. Okay, so depending on how much often they happen. Okay, so depending on the shape of the distribution, we're going to call them differently. But usually the shape of the distributions are going to be given using so-called mass function. Okay, so the mass function is the distribution function for the discrete random variable, and this is a function which is simply going to tell you the probability of every single output of your experiment. Okay, for example, what kind of experiment we can do? We can do the experiment of rolling a die. Okay, so you've got 6 different outputs, 1, 2, 3, 4, 5, 6, right? And the probability mass function is going to simply tell you the probability of every single output. Okay, or we can do the different experiment. We can count the number of the students. Okay, and the number of the students might be, for example, for this group, there are like 40 students, right? The number of the students might be from 0 to 40, right? Everything possible, right? And the probability mass function is simply going to tell you what is the probability of having 0 student, 1 student, 2 students, 3 student, 4 student, and so on. Okay, the probability mass function is the function which is going to tell you the probability of every single output of your random variable. Okay, simple. Okay, so usually the sum of all of the probabilities is equal to the 1. For example, this is an example of the probability mass function. Or we can do this another one when you roll a die, okay? So when you roll a die, your output, your x, can take the values 1, 2, 3, 4, 5, and 6. So what is the probability of obtaining 1 when you roll a die? 1 over 6. Probability of obtaining 2 is 1 over 6. Do you know what is it rolling a die? So you've got a die, like 6-sided cube, and you're just rolling this, okay? And probability of obtaining 1, 2, 3, 4, 5, 6 are all equal to the 1 over 6, okay? So this table is simply called the probability mass function, or this function which is going to tell you the values for every single output of your random variable is called the mass function, okay? So usually so most of the time, so you see, so these are the theoretical examples when we're talking about the rolling a die or tossing a coin. But if you go to the empirical cases, like if you remember in our previous lecture, lecture 3.1, we talk about the empirical probability, if you watch this. So most of the time in practice, we deal with the random process, which is not theoretical. I mean, in order to explain this process, we need this kind of table. Okay? So we're going to do a couple of examples, and I hope that this is going to be much more clear for you. What does it mean, the probability distribution? So let's say I've got a spinner, and I'm going to split the spinner into the 2 parts. 1/4 area of the spinner is going to be denoted as 1, and the rest is going to be denoted as 2. I'm going to rotate the spinner, okay? So what kind of result, and the result is going to be the random variable, okay? So what do you think? Is it the discrete random variable or the continuous one? Discrete, right? You can take either 1, either 2. That's it, okay? So there are 2 possible outputs, and I'm going to create the probability mass function for this random variable. So I'm going to just put simply x can take the values either 1, either 2. What are the probabilities of obtaining 1? So if you rotate, what is the probability that you will obtain 1? 1 over 4, because the 1 over 4 quarter area of the spinner is denoted as 1. And probability of obtaining 2 is 3 over 4. Okay? Oh, please note that the sum of the probabilities is always equal to the 1. Always. Okay? This is one of the most important features, most important properties of the mass function. Okay? The sum of all of the probabilities should be equal to the 1. So probability of x is equal to the 1 plus probability of x is equal to the 2 is equal to the 1. Okay? If you remember, all of our previous examples also fulfill this property. Okay, so this table is called the probability mass function. This is going to be the full description of our random variable. So if I say, can you explain me or can you describe me a random variable, you're going to describe it using this table. Like, I mean, if I say, hey, can you describe me this person, you're going to describe this, right, somehow. And the description of the random variable is going to be done using this kind of tables. Okay? Huh? Yeah, so if it is continuous, we're going to describe this using continuous functions, which are called the density functions, and we're going to talk about this next week. Okay? So now I'm going to change the experiment a little bit differently. I'm going to rotate the spinner twice. Okay? And the result is going to be, and the random variable is going to be the sum of the 2 results. Okay, could you please explain me? Could you please describe me this random variable? Can you do this? Or can we do this together? So if x is the sum of the 2 results, if x is going to be the sum, what kind of values it can take? No, sum. 2, 3, or 4. Right? It can take only 3 values. Yes? Do you understand this? The sum of the 2 results. Okay? So let's find all of the probabilities in order to make the table. So the probability of x is equal to the 2. It is when you're going to obtain 1 in the first trial and 1 in the second trial. Okay, it is going to be equal to 1 over 4 times the 1 over 4, it's 1 over 16. Okay, I'm just going to make the table here to write down all of these results. So the x can take the value 2, and its probability is 1 over 16. So at the same time, x can take the value to be equal to the 4. In this case, it is the same as when you get the 2 in the first trial, when you rotate this first time, and 2 in the second trial. So in this case, the probability is going to be equal to what? 9 over 16. So the probability of obtaining 4 is 9 over 16. And the probability of obtaining 3 is going to be equal to when you get 1 in the first trial and 2 in the second trial. It is going to be 1 over 4 times the 3 over 4. It is going to be 3 over 16. So 3 is going to be 3 over 16. Okay? And this is going to be the probability mass function. Oh, yeah. Yeah. Overall is not 1. It's okay for this case. Huh? Yeah, well, so I mean, this table is wrong, right? Because the sum is not 1, right? If you sum the 3 numbers, it is not 1, right? It means that we made this wrongly. Okay, so why this is wrong? Because we didn't count this probability correctly, right? Because this is not only the one case when we obtain the 3, but there is another scenario when we obtain the 3, right? And this is going to be equal to, so this is wrong here, so you're right. So there is another situation when we're going to get the P of 2 and 1, okay? So in this case, it is also going to be 3 over 16, so that is why I'm just going to multiply this to the 2. It is going to be 6 over 16, okay? So this sum should be also, do you understand why this is 6 over 16? Because probability of getting this case is 3 over 16. Probability of getting this case is 3 over 16. So the sum is going to be 6 over 16. Okay? But even if you don't know what is this, you can easily find it. Okay? Because you know that the sum should be equal to the 1. The sum of this one and this one is 10 over 16. So that is why it should be 6 over 16. There is no other way. Okay? The sum of all of the probabilities in your probability mass function is always equal to 1. Always. Okay? So now, just using this rule, we are going to derive the probability mass function for this a little bit more theoretical example. So here is the description of the full solution. So let's say now the probability random variable can take the following values. So you can take the values 0, 1, 2, 3, and so on. Okay? Oh, it might be like this. So let's assume that I'm going to make an experiment. I'm going to just go outside to the cross section there, and I'm going to count the number of the cars, which are passing every minute, for example. Okay? So what kind of values you can have? You can have 0 cars passing through this, right? Or 1 car, or 2 cars, or 3 cars, or 4 cars, and so on. Okay? It appears the probability of having the number of the cars to be equal to the I is equal to some constant times to the 2 in the power of I divided to the I factorials. Okay? What does it mean? It means that the probability that there will be no cars passing through in that minute, in a particular minute, is going to be equal to some constant times to the 2 in the power of 0 divided to the 0 factorials, which is C. Okay? Probability that there will be like a 1 car there passing through there, it's going to be C times 2 to the power of 1 divided to the 1 factorial. Probability that there'll be 2 cars, it's going to be C times like a 2 in the power of 2 divided to the 2 factorials, and so on. Okay, so this is like a very powerful function which is going to tell you the probability of every single output of your random variable. Your random variable is the number of the cars passing through that cross section every minute. Okay, and this is random, and it might take the value starting 0. I mean, it can be negative, right? It can take the value starting 0 until some number. It doesn't matter what is that number. Okay, so now the question is, so is it the proper mass function? What do we say by proper mass function? Yeah, if it is sum of for all of the values is equal to the 1. Well, is it the proper one? Well, we don't know, but we can make this proper. Okay, because C is a constant, right? So we need to choose the proper value for the C so that this becomes the proper mass function. Okay, it is very important, and it's kind of a little bit theoretical example, but this is one of the really important distributions, discrete distributions. It is called like a Poisson distribution. I'm just going to announce this before, but we are going to discuss this in more details next week. Okay, so this is called like a Poisson distribution. It is written like this, Poisson distribution. Sometimes I call this Poisson distribution. Yeah, Poisson. Okay. Yeah, so let's solve this together. I'm going to do this in this way. So I've got the probability of x is equal to the I is equal to c times 2 in the power of I divided to the I factorials, right? To the I factorials. And I also know that the sum of all of the probabilities starting from 1 to the infinity should be equal to the 1, right? This is the same as the summing of I from 1 to the infinity of c times 2 in the power of I divided to the I factorials, and this should be equal to the 1. From here, I need to find what is the c. Is it clear what we are doing at least? Yes? Okay. So the sum should be equal to the 1. Okay. Now, if you remember in the course of Calculus 2, for some of you, we discussed about the series. Okay. So do you remember what is a series? That is the sum of the infinite sequence, right? Okay. So this is the sum, right? Infinite sum, right? And this is the series. And we can know what is this, okay? So do you remember we discussed about like a different type of the series, like a Taylor series, a Maclaurin series, or like a Fourier series, right? And what is the Taylor series? It is when you can expand any continuous function into the polynomials, right? And you can do this with the exponential functions, with the trigonometric functions. Okay? Do you understand what's going on? So you can express any function as the polynomial. Okay? And it appears you can do this with the exponential function. Okay? So do you remember what is the expansion of the exponential function? Taylor expansion of the exponential function? Okay, it's okay. So let's do this together. So do you know what is the derivative of the e to the power of x? E to the power of x, right? Okay, so I'm going to do this in this way. So our goal now is to write down e to the power of x as the polynomial. Okay? So do you remember what is the polynomial? It is the like a linear combination of the power functions, like x in the power of 1, x in the power of 2, 3, 4, and so on, multiplied to some constant and added. Okay? If you don't remember what is the Taylor series, there is one like a very cool trick about getting the Taylor series for the e to the power of x. Okay? It works in this way. I'm going to write down the e to the power of x to be equal to the 1. Okay? Then in the next line, I'm going to write down e to the power of x to be equal to the 1 plus something. Okay? So that if you take the derivative from the whole thing, from the second line, you're going to get the first line. Okay? So what is the derivative of the left-hand side in the e to the power of x, in the second line? Of the e to the power of x, right? So what I have to add here, what I have to put here, so that the derivative of the right-hand side part is going to be equal to the 1. X, right? What is the derivative of the 1 plus x? 1, right? Okay. I'm going to do now the second line, third line, sorry. I'm going to do this. E to the power of x, 1 plus x plus something, so that if you take the derivative of the third line, you're going to get the second line. What I have to put here? X squared over 2, right? Because if you take now the derivative of the right-hand side part of the blue line, you're going to get the black line, okay? Can you continue? So now can you guess what is the series of the e to the power of x? What is going to be the next line? It's going to be 1 plus x squared over 2. What I have to put here so that its derivative is going to be this one? X in the power of 3 divided to the 6. Okay? What's the next one? X in the power of 4 divided to the 24, because the derivative is going to be x cubed over 6, right? What is the next one? X in the power of 5 divided to the 120, right? Do you understand how I'm constructing the next one? Because the derivative of the every next one should be the previous one. Derivative of the x is 1, derivative of the x squared over 2 is x, derivative of the x cubed over 6 is x squared over 2. Do you see this? Okay, so this is the Taylor expansion of the e to the power of x. Okay, and this is the reason why, for example, the e is 2.71. Okay, so you can take. Do you know why? What is the value of the e? Yeah, so how I can get the value of the e from the left hand side? By just substituting x to be equal to the 1, right? So just substitute x to be equal to the 1 to the series. What you get? So what you get on the left hand side? E. What you get on the right hand side? 1 plus 1 plus 1 over 2 plus 1 over 6 plus 1 over 24 plus 1 over 120. Or you can just take the 6 numbers here. And if you just add them, you're going to get 2.721. Okay? So the reason why we are writing is this sum is very similar to the expansion of the e. Okay? Can you tell me what is the, so let us expand this for some value of the I to be equal to the 1, 2, 3, 4, 5, and so on. Let me write this. If I is equal to the 0, what is this? 1. Oh, I'm taking c out of the brackets, okay? So without c. If I is equal to the 1, it's going to be 2. 2 in the power of 1 divided to the 1 factorial, right? If its power is equal to the 2, if I is equal to the 2, it's going to be 2 in the power of 2 divided to the 2, right? If I is equal to the 3, it's going to be 2 in the power of 3 divided to the 6. If I is equal to the 4, it's going to be 2 in the power of 4 divided to the 24. If I is equal to the 5, it's going to be 2 in the power of 5 divided to the 120. Right? Do you understand this? So here, I'm just substituting I to be equal to the 1, 2, 3, 4, 5, and I've got this series. Right? So what is this? Can you guess? E squared. So this series, it appears as simply e in a square. Okay? You can take out the c out of the brackets, and the rest is going to be simply e in the power of 2. Okay? Cool. So I'm going to do this. C multiplied to the 2 in the power of I divided to the I factorials. I go from 0 to the infinity. That is going to be c times e in the power of 2. Okay? And this should be equal to the 1 because we know that the sum of all of the probabilities should be equal to the 1. Okay? And from here we can easily find the c is going to be equal to the e to the power of minus 2. Okay, because e squared goes to the right hand side part. And that's going to be the probability. And if you would like to now evaluate what is the probability of x is equal to the 0, you are going to simply substitute 0 instead of, do you remember? P of x now is going to be c is e in the power of minus 2, right? Times the 2 in the power of I divided to I factorials, okay? And if you would like to evaluate that x is equal to the 0, it is going to be 2 in the e to the power of minus 2 times the simply 2 in the power of minus 2. Okay, so this is about the probability mass function. So in our next lectures, we're going to discuss the other type of the distributions. Okay, this was an example in order to show you one of the fundamental properties of the mass functions. So that the sum of all of the values of the mass function should be equal to the 1. Okay, cool.